Alright class, so this is the explanation video for exercise 6.9, which shows up on page 245 of your textbook. This is a great question. This is very similar to the questions that we did in class today, but really talks about the transfer of energy. That's what we've been talking about. One system is going to transfer its energy completely to another system. This is just another example of a problem like that. So far I've just written down all of the relevant information from the question. I would recommend you read over that question on page 245 and to see sort of how I picked out this information. So read the words and then sort of maybe even write out, this starting material by yourself, and then compare it to what I've written down. So I've got 33 milliliters of this 1.2 molar HCl. So right away, I'm looking at this, I'm seeing a volume, I'm seeing a molarity. In my mind, I'm saying to myself, well, I can solve for the number of moles of HCl is added to 42 milliliters of excess sodium hydroxide. So that just tells me that the limiting reactant in this reaction is going to be the HCl. The T initial is given as 25, the T final is given as 31.8, and I'm asked to find the delta H, the enthalpy of this reaction. So here they've also given me this full reaction where my HCl will react with sodium hydroxide. I'm going to form sodium chloride salt, which will be dissolved, and form water. This is going to give some energy off. I know it's going to be an exothermic reaction because I see that my temperature has gone up. So right away, I'm thinking to myself that this delta H, it's going to be negative, right? In my calculations, I might end up with a delta H or a Q value that's positive. I might get confused by the signs. But the first thing I'm going to do, I'm going to say, well, I know that this delta H has to be negative because this solution gained energy, right? It gained energy because the temperature went up. So keep that in the back of my mind as well. It tells us to make some assumptions. So here the heat capacity of the solutions and density are the same as water. So that heat capacity, 4.18 joules over grams times degrees Celsius. So make sure you pay attention to the units there. And then the density of water, 1 gram per milliliter. So I can just use grams and milliliters sort of interchangeably. All of the energy goes to heating the solutions up, no cup contribution. So in lab, and sometimes we've talked about, that the cup needs to be heated up as well. In a lot of these problems, especially that we're going to see on the exam, we're just going to assume that that cup has no contribution or that it's very well insulated. So all of the energy that's lost by the reaction or given off by the reaction is absorbed by the solution. Okay, so for the water, or the solution, we're going to say that Qcal, and I'm going to say Qcal because we can imagine this as a calorimeter system where we've got a water solution, equals 4.18 times 75. Now this 75, that comes from 33 plus 42, that should equal 75, and that's my number of milliliters, but like I said, 1 gram per milliliter, so that's going to be 75 grams in my calculation here. And then for my delta T, 31.8 minus 25. So that's going to be my T final minus my T initial. And I can go ahead and just do this calculation, and I get to 2131.8 joules of energy. And this is going to be the energy that is absorbed by the water, right? By the water solutions. We'll put it in solutions. So this is a positive value, right? That tells us, let's put it there. This is a positive value. That tells us that this energy was absorbed by the solutions. The temperature went up, right? So we're putting energy in to absorb that energy, make that temperature go up. Okay, now Qcal should be equal to minus the Q of the reaction. And sometimes we write minus Qcal equals Q reaction, but as long as we have a minus sign somewhere in there, that's going to make it so that those values are the same, right? So if I say that the Qcal is equal to minus Q of the reaction, then that means that the Q reaction is going to be minus 2131.8 joules, right? So this is saying that the reaction that we did way up here is giving off this amount of energy. So the value needs to be the same, but the sign should be different depending on the point of view that we're looking at it from. From the point of view of the water, the calorimeter, it's gaining energy. From the point of view of the reaction, it's losing that same amount of energy, but the sign is going to be negative because it's giving that energy away. It's evolving that energy. Therefore, the last step, if I want to solve for the delta H for my reaction. That's going to be my Q reaction over the moles that I actually used in this reaction, right? So that's where the moles of HCl is going to come into play. So over here, I'll just do a quick calculation for moles. That's going to be my 0.033 liters times my 1.20 molar solution. And that's going to give me 0.0396 moles of HCl that I consumed in my reaction, because in my reaction said that that was the limiting reagent, right? We had excess sodium hydroxide. So this is my number of moles. So for my delta H of reaction, and that's going to equal minus 53.8 kilojoules. And that is my final answer. Here I skipped a step. Oh, you guys can't see it again. I skipped a step going from joules to kilojoules. So this would really be 53,000 kilojoules, but sort of just skipping a step there. This number of joules divided by moles, that's going to be the amount of energy that the delta H, the reaction, will give off. So to finish this off, what I want to do is I want to redraw my thermochemical equation. So HCl aqueous plus sodium hydroxide aqueous goes to sodium chloride plus water, and my delta H for this reaction, so per 1 mole of HCl minus 53.8 kilojoules of energy, will be evolved. So this is my full thermochemical equation. This is the nice way to write the final answer. And I just want to do one last sort of run through, sort of check, okay? This is an exothermic reaction. I know that it's an exothermic reaction because my temperature increased. This temperature increase tells me that I'm going to have a negative delta H. Energy is going to be evolved when I do this reaction. Here I did my Q sort of treatments, and my Q reaction I have is minus 2,131 joules of energy. This Q reaction is negative because from the point of view of the reaction, right, my reaction, I'm giving energy off. That energy is going to be absorbed by the water solution, so it's going to absorb the same value but the opposite sign of energy. So the Q value for the calorimeter from the point of view of the thing that's heating up, gaining that energy, is going to be positive, and this calculation here sort of just shows me that. Sometimes you're going to get confused with this. You're going to get confused with, is it negative, is it positive? It really shouldn't matter though. Really, when you get to your final answer, right, the values are going to be the same all the way through, regardless if you have minus or positive. But when you get to your final answer, you should be able to figure out, and you should be able to say to yourself, well, is this an exothermic reaction? Is this an endothermic reaction? What's happening to the temperature, right? I should be able to figure out what's happening to the temperature. That tells me that this must be a negative value, an exothermic reaction. All right.